Guys, I don't know about you, but I got my coffee fresh from the press. That's right, I use a French press. Grind my own beans with my bare hands like a real man, and then I put a bunch of creamer and sugar in it. Alright, this is episode 1, Pushing Voxels Forward, season 2. I am ready to start. I've been ready to start this since season 1. I really enjoyed doing season 1. Ran into some issues, discovered some new things, was researching, and we're gonna kind of forget season 1, and this is why it's season 2. And just like last time, I'm gonna go ahead and start by running this project. Now this is a project called Voxel. It's been my main focus for quite some time. As you can see, it's nothing special. It's actually just a plane, but I'm gonna go ahead and I'm going to tweak a couple of settings here, and I'll just dive right into it. Voxel is a path tracer that I've been working on. I don't know why the building area is so small. It's usually a lot bigger, but yes, this is a path tracer that uses global illumination and aims to solve the render equation. It uses optics 6, and just to show that it's using voxels, it's actually using whole single color voxels. As you can see here, individually they're little tiny cubes, and this is the Stanford bunny, just imported. We can also, oops, I didn't mean to, oh great, I just messed everything up. We can carve into the bunny like this, deform it. And as you can see, when I dig into it and the sky, which is just white at the moment, doesn't hit it directly, it's actually dark. And again, that's using path tracing. And I'm using a couple of different filters. I'm using a temporal filter, a wavelet, a Trous or a Trous wavelet filter. I'm using basically a variation of the spatial temporal variance guided filtering. I have a whole other video on my channel if you want to learn a little bit more about it. But that's what I'm using here. And I'm using a highly downsampled resolution because I think it looks pretty good. I don't think it looks bad. Overall, I'd say that this looks great. However, I do not like the blurring look of SVGF, and so more on that later when I discuss what we're going to be doing. But yeah, in short, this is just a project that I've been working on. I'll showcase a couple other quick things just to try to grab your attention a little bit. So like we could place lights like this. These voxels here all emit this color light, whatever that is. And if I were to turn the skylight off, as you can see, it emits light, and there are even shadows that get cast. So I'm actually going to make this a different color. Lights can be any color you want. That's the beauty of path tracing, is you get all these really cool effects. Like this shadow right here that's being cast from these lights. And I think right now I don't have any bounces enabled because bounces are really hard to denoise, and again, more on that later when we get to it. But that's this project. Really cool. I like it. Got really far, but I decided I wanted to redo the path tracing. Now that I have a little bit of path tracing knowledge under my belt, I wanted to restart it, and I figured why not make Pushing Voxel Forward Season 2 about path tracing and other voxel techniques, more dominantly GPU techniques. So we're also going to be hopefully focusing on fluid physics one day after we get the path tracing and the denoising and all that exciting stuff. If you don't know what path tracing is, you've been living under a rock. Path tracing, well, I'll just get into that another time. Alright, so like I said, that last project used NVIDIA optics. I'm going to go ahead and run another path tracing project that I worked on that does not use optics, that actually uses CUDA and my own ray tracing. I'm just going to bump this up real quick. So before I go further, this does not have denoising, which is why it looks like garbage. But this is a project that I called VTraceX, despite the name saying Voxel. I just never changed it. And this is also a voxel path tracer, but right now it really is only a ray marcher, and it uses rays and Monte Carlo sampling to determine ambient occlusion, which is a variation of or kind of a part of global illumination. It can get you what's the word, propagating sunlight. So but I'm bringing this project up for a couple of reasons. First off, because this is actually the basis of what we're going to be using, not the optics project. We're actually going to be combining these two, but this project had some really cool tech because what it does is it has a hybrid rasterizer, a triangle rasterizer. It has a splatter if you wanted to splat voxels, and it also has ray tracing to render. So right now I have it set so the rastered part is actually rendering triangles. That's why you can see that up close stuff isn't made of voxels anymore. It's actually got the dual contouring triangle meshes, and then in the distance there we can see the cubic voxels. And as I move the camera, we can see where it changes, and that's all optional. I just wanted to experiment with triangles to see how it would work. In the project that we're going to be working on, I don't know if I'm going to be supporting triangles. I actually want to try to have the triangle support as well as the voxel support. We're not going to be doing a hybrid. I just want to be able to turn on both depending on kind of the scene that we're looking to build. I really like the solid color voxel look, but again, you know, who knows? Our main focus is going to be path tracing for a little while. Real quick, one of the things that I wanted to touch on is I'm using the RTX 2070 card. I believe that will be good enough to do everything that we want, at least as far as path tracing goes. With ray tracing, unfortunately, it's not just cut and dry like NVIDIA made it seem. In all of their presentations showcasing the card, we actually have to do a lot of the work ourselves, including the denoising. I would like to try and use the AI denoiser. I was unsuccessful my first times, but again, more on that when we come to the denoising. Alright, so with the history out of the way, let's go ahead and get into the meat of what the series is going to be. Again, like I said before, it's going to be path tracing. And so I whipped up a quick diagram here using the tablet that I bought a while ago, specifically for this video series. I know I could have typed this, but I've always wanted to kind of draw diagrams and stuff. So probably going to be seeing a little bit more of this. And I apologize if my handwriting is sloppy. I'll read it out and hopefully you guys are able to make it out as well. So here's what our path tracer is going to entail. It's going to use an input of an albedo, depth, normal, materials. So this means it can be render agnostic. We can either use rasterization, splatting, or ray tracing. In the path tracer that I showed you, everything used, or the voxely path tracer, everything used the ray traced input and then path trace immediately after that. That's not good. You don't want to combine the two pipelines together. So that's why the stuff is broken up here, and that's part of where the VTraceX project is going to come into play. I would also like to separate the direct from indirect lighting. So what that means is we're going to be casting shadow rays in addition to our bounce rays, and that way we can filter them separately, and I think that actually results in better quality. And we can also turn off indirect lighting if we want to without having to affect the just number of bounces and overall path tracing. I would also like to implement bidirectional path tracing, or BDPT. What that is typically path tracers use what's called backwards path tracing, meaning we take the pixels on the screen and we shoot rays from where the camera is and then hope that it hits a light, and then that's our pixel color. Forward path tracing is like how light behaves in real life. Light sources like a light bulb or the sun will shoot rays out in random directions, and then whatever it hits, it bounces and eventually hits our eye. That doesn't really work at all for rendering, because most of the time a ray is not going to hit a pixel or hit the camera. And bidirectional path tracing combines the two, and as I'll show on the next screen, it converges a lot more quickly. And what I mean by converges is we're going to be using Monte Carlo sampling. Monte Carlo is a way of solving the render equation. And you know what? Actually, I'm going to go ahead and try to write that down here. Okay, so I decided to just take the render equation off of Wikipedia and paste it in here. I think that'd be a lot easier for both of us. I don't want to spend 20 minutes writing this all out when no one will be able to read it in the end anyway. So breaking it up here, I have actually color-coded different sections, starting with this one right here. This first color, L0, is going to be the output color. That's the color of our pixel, and it's equal to all of this. So this first part here is the emissive property of the material. So for example, if we're looking at a light bulb, it's going to be the color of the light that the light bulb is emitting, so probably a bright yellow or a white. The remainder of this function is actually just this integral here, which is the average of all the samples hitting the surface, and that's why it's actually represented as an integral, because there are infinitely many samples that could hit the surface due to the way that light behaves physically. In fact, if we look at the function, we see this Li, which I'll get into a little bit more later. That's actually recursive and is this part right here, so the function repeats itself. That's why we use Monte Carlo sampling, because we have to solve the integral, what's the word, analytically. We have to, take physical samples and average them out over time. So I'll start with this first one right here. This FR is actually the bidirectional reflectance distribution function, which is what this is, the BRDF, and that basically defines how light behaves when it hits the surface, whether it scatters entirely or reflects or just has a specular highlight or is a glossy surface or what. So for this next part here, recall that I said this integral is the average of every single sample hitting the surface. Since we are solving this analytically, we're testing one ray, then the second ray, then the third ray, fourth ray, so on and so forth. This Li is just the light value of the returned ray that we're shooting out. So for example, that could be for the first ray, we shot it out, it hit a wall, it bounced, it hit another wall, we cut our path tracing off at 2 bounces, it returned black. For the second ray, it could be the light, or the ray hit a light and now it returns white. That's all this is. This Li is whatever value or light value that ray returned, which is this whole thing all over again. All right, and that actually ties into the final part, which is this part right here, this purple part, which doesn't actually include the delta direction. That's what this is here. The Wi is the direction of that ray. It's more of just this part here, which is the dot product between the ray direction and the normal of the surface. So again, that's kind of where the cosine weighted BRDF comes in, because a ray hitting a surface perpendicular is going to have more of an effect as opposed to a ray hitting parallel to the surface, and that's why, because of this part right here, that dot product. If you want more technical definitions of this, I recommend reading the Wikipedia article. I'm not very good at describing or explaining this stuff, but basically that's what the rendering equation is the emissive property plus all the indirect or direct light, for that matter, hitting the surface and how that light responds to the surface's properties. So that being said, we can actually move on in our list, and the next item here is multi-importance sampling. And what that is basically a way of reducing variance in our rendering. I will try to describe one basic example. So light hitting a regular diffuse surface, light that hits almost parallel to that surface's normal won't have as much of an impact as light hitting perpendicular to that surface. And so when we're doing our backwards ray tracing or backwards path tracing, we are wanting to have more samples or rays perpendicular to that surface's normals, because they'll have a greater impact on the light that that surface receives versus ones that are almost parallel to that surface. Actually, so that's just importance sampling. Multi-importance sampling would be combining another ray direction bias. So that would be like tracing a ray towards a light. If we had that light information in the scene, we could just trace directly to it rather than tracing in a random direction and hoping to miss that. Again, I'll show that in the next slide where I have examples of kind of what all of these are. Next up, I'd like to have simple BRDF definitions. BRDF stands for bidirectional reflectance distribution functions. You can see why I didn't write that out. Again, coming from here, that just defines how our light reacts when it hits the surface, whether it's like a glossy surface, diffuse, or reflective surface. We want to be able to define that easily and not have to write multiple functions in our path tracer. Then this next thing here, I kind of just threw in there because it's something that I was interested in. Rather than using purely random numbers, we use blue noise. And I've read or heard kind of in papers that might reduce variance and lead to converging samples. But again, it's just something to maybe play with in the future. And last up here is denoising. Obviously, path tracing, Monte Carlo sampling, produces a noisy output. I don't want to rely heavily on denoising because typical standard denoising algorithms don't produce the best output. Obviously, you've heard of the saying or the phrase work smarter, not harder. That's what all of this is for. A lot of the path tracers out there rely on just one sample per pixel. I'm counting on our engine having more than one sample per pixel and also better samples per pixel to reduce our reliance on denoising to get an acceptable output. But again, more on that later when we actually do our denoising. All right, on this slide, I have a bunch of examples of properly sourced images that I did not just find in Google Images or Wikipedia. This one I did get from Wikipedia. These two right here, I got from, I think it was an image on some Stack Overflow computer science or software engineering thread. And so if these are your images, I apologize. I didn't see citations and they were perfect for what I wanted. But anyway, please don't sue me. Let's go ahead and get into what this all is here. So the Cornell box is the tried and true method of testing path tracers. It demonstrates a variety of global illumination effects, I guess you could say. So it's really simple. It's got a red wall on the left, a green wall on the right, couple boxes in the middle, and a light at the top, and then the other walls are white, and it showcases that light lighting up the faces of the boxes, also casting shadows on the walls, and then the colors of the walls bouncing onto the nearby faces on the boxes. Below that is a variation of the Cornell box. It shows 3 different balls or marbles, each with different BRDFs. On the left here, we have mostly diffuse. On the right here, we have a glossy reflective material. In the middle here, I'm not really sure what that is. I think it's refractive or purely reflective. Again, I'm not sure. It could be both, but it's showcasing 3 different materials. In the middle here, I have an image that showcases purely backwards versus bidirectional path tracing. And it looks like I actually got my images mixed up. So the bottom one is just normal path tracing, backwards path tracing. The top one is bidirectional. The way that bidirectional path tracing works is, like I said before, it will trace backwards rays like normal. If it hits a light source, great. If it doesn't, it will trace rays from the lights, do a couple of bounces, and then try to ray trace from where those 2 paths stopped. And if it does, then we have an active lit sample. It's more expensive to compute, but as you can see, after 1 minute, the backwards path tracing is significantly more noisy than the bidirectional one is. Over here, we have the naive Monte Carlo sampling versus multi-important sampling. Earlier, when trying to explain this, I gave the example of sampling, shooting rays towards the light source and also using cosine-weighted ray distributions. Now, I think that this image is kind of unfair because it uses sampling the light source and then sampling the BRDF, and then this middle one clearly doesn't look as good as the one on the left. This would look a whole lot better than it would if you just shot rays randomly in the hemisphere for that surface. But if you combine both, that's when you get multi-important sampling, and obviously on the right, we have a better input than the one in the middle, and the one in the middle is way better than what we would have if we didn't have any important sampling whatsoever. All right, and lastly on the bottom right here, we have the denoising example, which is from yours truly, the Voxel project. It actually uses the same voxel scene, and it uses the H-Rouse wavelet transform filter on top of a temporal filter, which gives pretty good results in at least this specific image without the camera moving too much. The problem with denoising is details get over blurred and lost in this case and bleed over edges and stuff. It's a really tricky problem to solve, but again, that's just the example of what we can expect. So if we have something that looks like this, and then something that uses multi-important sampling, if we throw denoising on top of that, I believe that we could get some pretty good results without having to rely too much on the denoising. It's mostly just a way of cleaning it up. Alright, so with the crash course in path tracing out of the way, hopefully you understand a little bit about what we're going to be trying to do. In the next episode, we're actually going to be starting work on this project, and what we're going to be doing is taking a bunch of what I've done for Voxel and a bunch of what I've done for vTraceX, so we have kind of a base to work off of. We're going to have a dynamic voxels, we're going to have a scene that loads chunks dynamically, we're going to have optics set up. We're going to be using optics for this project, by the way. And then we're also going to have support for triangles. We're going to have the albedo, normal, material maps all set up for us. So all we have to do is actually write our path tracer. I think it's going to be a lot easier in the long run, but we're going to begin work on that in the next episode. Guys, thank you so much for watching. I really appreciate it, and I'll see you next time.